Så jag börjar. Hello, my name is Alexander Hansson and I'm a physicist working for Orexplore. So the topic of the talk today is extracting the maximum amount of information from drill cores, subtitled Structural Geology through X-ray Tomography. So this talk was also supposed to be given by our R&D manager, Mikael Bergqvist, but unfortunately he cannot join us here today. So what is the kind of ultimate analysis that you could do on drill core? Well, you might end up with a wish list that looks something like this. You want the analysis to be fast, to be able to make use of the data as using as little resources as possible. You would like the concentrations of all the elements in the sample, as well as to know in which minerals are these elements located. Moreover, you may be interested in things like densities and definitely the possibility to identify structures in the sample. And not only identify them, but also measuring the orientation of planes and the direction of lineations. Grain size distribution is another property that you might be interested in. And when doing all these things, one would like to sample the entire volume of the drill core, ideally, and also be able to preserve all the spatial information that you have in there. So what can Orexplore's technique, the combined tomography and XRF technique, deliver when it comes to this? So I will start off by explaining a bit about tomography. So up here you see an X-ray image of a drill core in analogy to the medical X-ray image that you're familiar with. So in this image, the darker areas blocks more X-rays. In this video here, you see these X-ray images taken from a lot of different angles. And when you have done that, you can apply elaborate algorithms and powerful computers to reconstruct the 3D attenuation of the sample. So attenuation, that is the ability of the material to block X-rays. So what you see here on the right-hand side is simply a data cube where I have changed the transparency and the color depending on the attenuation. So the material with the very lowest attenuations are transparent, and then you decrease the transparency and change the colors from gray to red to yellow, and that is the most attenuating material. And when speaking about tomographic images, we use the term voxel, which is nothing else but the pixel in 3D. So the attenuation is a property which depends only on density and chemical composition. And in terms of chemical composition, the higher atomic numbers you have in your material, the more it will block in general. So if we look at this scale here, air has, of course, a very low attenuation. If you look at common rock-forming minerals like quartz, it's higher, of course, and then biotite is higher than quartz. And this is interesting because micas are minerals that are important for structural geology because they can alter their shape in the metamorphic processes. If we go further up the scale, we encounter iron-rich minerals like pyrite, and then further on things like slab-varite and galena, which contains even higher atomic number. And it turns out that gold is actually one of the absolutely most attenuating materials because it has a very high density along with a very high atomic number. So you could also do the inverse here. Like you have a sample, you you obtain tomography of your sample, and then measure the attenuation in all the voxels. And then you can see where on this scale is my measured values to get an idea of what minerals do you have in your sample. It's not a perfect measure of minerals because there's 4,000, more than 4,000 of them. So you could have multiple solutions. But in general, it gives you quite a good idea about what minerals you can have in your sample. And here it also helps with the XRF signals that we obtain with our machine to differentiate among these. So for the tomography, we also want to preserve orientation, and this is done by in the following way. So you load your core into a sample holder like this with the Orexplore loading station. And this is for puzzled core. So you would have some orientation mark or bottom of hole line. And in this sample holder, you can rotate the lid so that this metal piece is aligned with your orientation mark. And then the machine will register the position of this metal piece, and you will set your coordinate system for the tomography. Now over to measuring structures. So here we have a tomographic image with more attenuating areas in red and yellow. So what you would do here is that you would rotate the core around its axis until your plane, you view the plane edge on. And then by clicking twice, you draw a line that will define your plane. And when doing so, you are measuring the angle to the core axis, the angle to the bottom of hole line, as well as down the hole depth. And these parameters can then be exported to your azimuth and dip for your hole. For lineations instead, we need to rotate in 3D, not only 2D, so that we view along the linear structure. So in this example here, you have a very nice fold. And there it's pretty good orientated. So here you can just click on the image to define the lineation. And when doing so again, you would measure the orientation to the core axis and the angle to the bottom of hole line, as well as the down the hole depth. So over to elongation. So here's a piece of core from Loviisa-gruvan. It's roughly 4 by 4 centimeters. In this tomographic image, again, more highly attenuating areas are color-coded in red and yellow. So what you can do is to apply a particle detecting algorithm on this data. And so this has been done, and here is an example shown here. So the blue dots are 3D coordinates of voxels belonging to the particle. And what you can do, like I've done here, is to draw a line along the major axis of the particle. And this can be done automatically for all the particles you detect in your volume. And on the right-hand side here, I plotted the orientation of these vectors on the stereo net. I won't go into detail to define what the stereo net is, but it basically shows you the orientation of these vectors then in 3D space. And you can see that for this this piece of core, the particles line up very nicely along a certain direction. And that's an important piece of information regarding the structure. And here you can also tune the range where you define your particles to match your favorite particle, let's say. If you want to study, say, how do the pyrite particles in which direction are they facing. So again, here you have the same piece of core, but instead of the elongation, you can look at the flattening. So you find the plane perpendicular to which you have the least extension of the particle. And this plane, it has a pole perpendicular to it, and you can plot that in the stereo net as well. And this can be done automatically and filtered to your particle of interest. And you also see that the flattening of these grains line up quite nicely in 3D space. Here is a different piece of drill core. It's again roughly 4 by 4 centimeters. You have lots of particles in there with a bit higher attenuation in red here. So what we can do is to simply measure the number of voxels that belongs to each particle, and that gives you a measure of the size of the particle. So on the right-hand side here, I plotted on the x-axis the number of voxels from 10 to 10,000, and the number of particles from 1 to 1,000 up here. And the different colored points are just particle in different attenuation ranges. In the Stream Index project, we scanned a large number of cores from Boliden, so from the Kristineberg, Åkela Kankberg, and Renström mines. And these images are just an example to show you the great abundance of structures that you can find in drill cores. So here are some nice examples of folds, foliations, veins, etc. So you might have thought, oh, tomography, it sounds like it's a lot of data, maybe that's an issue. Well, it's not actually. So here is a screen, is a photo of the screen of our machine, our product, the Geocore X10. And you can see up here that we have roughly 14 kilometers left of tomographic data of drill cores on our local server in Kista, where our headquarters. And here is a part of a screenshot of the Orexplore Insight software for a project where you have a number of holes that you've drilled. And simply by clicking on one of these holes, you get the tomographic data along with concentrations for that hole. So you have a fast access to all the holes in your campaign, all the cores in your campaign. And this data can of course be used in the modeling of your deposit, both the geochemical data as well as the structural data. So back to the wish list. So Orexplore's combined tomography and XRF technique using the Geocore X10. It can scan cores, so the standard scanning time is 18 minutes per meter, and it's decreasing without altering the quality of the data. You can also run faster and slower scans. You get the concentration of 65 elements through direct detection with XRF if they're above the detection limits. And you get some indirect detections of what minerals you have in your sample, and also the density. As we've seen in this talk, you can identify structures, both manually and automatically. And you can also measure the orientation of planes and the direction of lineations. And moreover, you can get the grain size distribution. These scans typically scan samples the entire volume of the material. If you have a tough case where you have a lot of highly attenuating material, like lots of gallinos, for example, even the X-rays won't be able to penetrate the sample. So in some cases, you don't get the whole volume, but typically. And when doing all of these things, we really preserve a lot of spatial information. Our product, Eurocor X10, has been released, and you can order scans or hire the machine. Thank you.